So in this class, let's start the topic of hidden Markov models. So the function of hidden Markov models is to analyze the sequences. So it may perform analysis, it may also perform prediction. So it may perform analysis and prediction of time series data. So what is the time series data? The data that changes with time. The data that changes with respect to time intervals. So I must say changes to regular time intervals. So something that is changing with respect to these regular time intervals. So this is time t0, this is t1, this is t2, this is t3, this is t4, t5, and so on. So some kind of data which is changing its states in every time. So suppose some state here, it is S, okay, or S1, the state is here S2, then it comes back to S1, then again S1. Sometimes it may not necessarily change, the state may remain the same, S2, S1, something like this, right? So as an example, the things that are changing with time, so tiny example can be like of on each day we have some kind of weather, either it is rainy or sunny, right? So we are assuming just right now two states. So one state is rainy and one state is sunny, right? So day 1 could be rainy, day 2 could be sunny, day 1 could be rainy, day 3 could be rainy, day 4 could be rainy, day 5 could be sunny, day 6 could be rainy. So this each day there is some kind of weather and that is changing at random, right? Similarly, we have these financial forecasting. On each day we have some kind of value of stock market and some other values also that can be obtained, right? Similarly, in recognition of time based motion, right? So on time based motion, suppose the car is passing and some camera is sensing, or some vehicle is passing and some camera is sensing, right? So with the passage of time, something is passing, something is not passing, so that some kind of problem can be developed in that way. And another very popular problem that is being applied in, that is speech recognition. Speech recognition. So speech is generated and the voice or all the things that are generated in speech, all those quantities change with respect to time, right? So speech can be again with respect to time, it can be again drawn some kind of like this, right? Now again, coming close to more NLP, or in terms of NLP, we can say that whatever we are writing, so writing text is also time based. So because our speech is also time based, we speak each of the words or letters one by one, right? So in conversation we cannot speak everything at the same time. So similarly, we cannot write everything at the same time. So the words that are being generated, that are also time based, right? So if I say that a word, a sentence, if I write a sentence, suppose hidden Markov model is a sequence model. Right, so you see each of these words are generated that change with respect to time, and here we have some kind of, you know, these so we have some kind of states, or rather we can say these are observations of some states, right? So we will be modeling how this becomes this sentence becomes a hidden Markov model, right? So another example could be optical character recognition, or more specifically character recognition. So handwriting character recognition or handwriting recognition. So while we are writing, so each of these digit, each of these letters, these also can be recognized, right? And they can be converted into digital text, right? So this is handwritten text, and that can be converted into the digital text, right? Something like this. So because this is also a sequence of letters, right? So these are something that are specifically related to NLP. Otherwise, any kind of problem that is time based, that can be dealt with the help of hidden Markov models. And hidden Markov models were those models that very at the early stage, they were modeling the sequences or modeling the time series data. So but currently we have the advanced models. After hidden Markov models, a lot of study on hidden Markov models, people came up with the CRF, that is the conditional random fields. And after again more research, the neural networks came back, and we have currently the state of the art, the LSTM based models, right? So initially the hidden Markov models 10 years back were a lot of into research, and then after that around 5, 6, 6, 7, 8 years back, the CRF was one of those most popular sequence models, and now this LSTM is currently, and variants of LSTM are currently the latest state of the art in sequence modeling. So sequence modeling is some kind of model that models the sequences, right? So we have sequence of states here, that's why we call it a sequence model, right? So let's see the first, what is a Markov model, or what is a Markov chain. So suppose we have some, again let's take the weather data. I say that some day is either rainy or sunny. So suppose day 1 is sunny, day 2 is also sunny, day 3 is also sunny, day 4 is suppose rainy, and day 5 is rainy, day 6 is sunny, and day 7 is rainy, right? So each of these are the sequence of days. So this is day 1 and day 2, day 3, day 4, day 5, day 6, day 7. So we move on from day 1 to day 2. Day 1 is all sunny, then day 2 is also sunny, day 3 is also sunny. So we represent this sequence like a chain. This is a chain of states, right? So day 1 is a state, or a day is a state. So we call this as a Markov chain. So this is Markov chain, right? So this is simply a chain, but we call it as a Markov chain because we apply a Markov property. Okay, so what is the Markov property? In the Markov property, we discussed that we see that this a particular intermediate state, any state, is depending upon its previous state, right? But not necessarily it may only depend upon the previous state, it may also depend upon some earlier state also, right? So this may depend on this also and on this also, right? So the Markov, the most common Markov property is that a single state is dependent upon only a single state. It means a given state is only dependent upon this previous state, right? So this is called as the first order Markov chain. So this is first order Markov chain, and in this we apply the Markov property as the probability of state, any state S t plus 1 given all the previous states st comma st minus 1 dot 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 s1 can be assumed as p of st plus 1 given st, right? So we are ignoring all these components, all of these previous states. So with the help of this assumption, this Markov assumption, we achieve the first order Markov chain, right? So we can have other assumptions also. St is dependent upon earlier two states, but in that case, in say higher order Markov chain, the things become, or the things get very complex, and there is lot of processing that is involved while training and while analysis of these kind of situations, right? So in all the cases, in most of the cases, generally first order Markov chain is utilized, and that works very, it works quite well, and there is not large improvement if we apply second order or third order Markov chain. So unnecessary giving a lot of computation time and not getting back as much as results that are expected, that must be expected. So in general, first order Markov chains are there, right? So now if we are having this Markov chain, right, so how do we move on to the next state? So what does it mean? So this means that st p of st plus 1 given st is actually some value, some probability value that is between 0 and 1. So that means if we are moving from sunny to sunny, there may be some probability value, right? Some probability value, suppose it is 0.8. So what does it mean? If I may write it more specifically with respect to this problem, is that p of st plus 1 is equal to sunny, right, given that st is equal to sunny. St is a state, okay, st plus 1 is another state. So I am taking up this transition, right? So in this transition, the previous state is also sunny, the next state is also sunny, and this is called as the transition probability. Transition probability, right? So I may take some other transition. Let's take this one. So this one is P of St plus 1 is equal to rainy given St is equal to sunny. So this may be another probability value, right? So this was sunny to sunny, the first one, and this is sunny to rainy, right? So actually we are calculating the probability of sunny here, but it is conditioned on sunny, right? The next state is sunny and it is conditioned on sunny. Next state is rainy, it is conditioned on sunny. So we may say that the states are moving from this previous condition to the next condition, right? This is actually, the arrow is the arrow is like this, it's moving like this, right? So arrow is like this when we write in probability, right? It is sunny to sunny, it is sunny to rainy here, right? So sunny to sunny is, I said, it may be some value that is 0.8, right? So sunny to rainy, again it may be also some probability value, right? So since we are having this of St plus 1, that's the same probability, right? Same state, same random variable, it is having two values, that is, one is sunny and one is rainy, right? So we can just directly calculate P of St plus 1 here, right? And this is also P of St plus 1, and we are having only two values, that is, one is sunny, one is rainy, so the other value would be 0.2, that is 1 minus the previous one, right? Similarly, we can have more probabilities associated here. So P of St plus 1 could be sunny given sunny, that is done. P of St plus 1 could be rainy given rainy, and sunny given rainy, right? So let's draw it in the form of Markov model. So we represent a state here as rainy, we represent the state here as sunny, right? We say that when there is a transition from sunny to sunny, same state, the probability is 0.8, right? When we say that there is a transition from sunny to rainy, the probability is 0.2, right? So these two probabilities sum up to 1. Similarly, when there is from rainy to sunny and rainy to rainy, suppose rainy to rainy is 0.6 and rainy to sunny is now 0.4, right? So this sequence is actually a Bayesian network. We are not going into those details, but it has actually this Markov model and Markov chains. Markov models. This is the Markov model, and these Markov chains are the realization with respect to time of this Markov model, right? So in this Markov model we are not able to see the time, but in this chain, so when we see with respect to time, it is called as a chain, and this chain is actually some time based Bayesian network. So these are Bayes networks, and the characteristics followed in this Markov chains and Markov models is actually the Bayes characteristics. We are not going into those details. What is a Bayes network? So Bayes network is actually a network in which some random variables are associated with each other with the help of probability values, right? So now what could be the problem? The problem could be I may be given a sequence, some sequence. Suppose I let me take the same sequence S S S R R S R. So S S S, then R R S R, R R S R. So I may be asked to write down the probability of this sequence. What is the probability of this sequence? Right? This is one kind of problem. So how would I write the probability? I must see that I can represent this Markov model with the help of a probability table. I can write this. So suppose this is t minus 1, this is t minus 1, and this towards this side, this axis, I am taking the time t, and this is, suppose it's rainy, and this is sunny, this is rainy, and this is sunny. So if we can also take it t plus 1 and t. So here we have taken t plus 1. So it's actually the same thing. If we can write this as, we can write the same thing as p of s t given s t minus 1. Both are the same things. In some books you will find s t given s t minus 1. In some books you will find. So t is actually the current state, t plus 1 is the next state, t minus 1 is the previous state. So this table, this may also be written as t plus 1, and this may be written as t, right? So both are the same things. So going from rainy to rainy, okay, so rainy to rainy is 0.6, rainy to sunny, okay, is 0.4, okay, sunny to sunny is 0.8, and sunny to rainy is 0.2, right? So this whole thing can be represented by a single probability table, right? And so this table is called as the transition probability table. This is the transition probability table of HMM, right? So this is the transition probability table. So we can use this table, So this is the table here, and with the help of this table we may calculate the probability of this complete sequence. Right, so how do we calculate the probability? So if we apply, so this is like this in more clarity. If I write it like these are the random variables and I am separating it by comma. So if I apply the chain rule here, okay, so P of S given SS RR SR, right, dot P of, then if I apply the chain rule, okay, then it will be a very complex one. But what we are doing is that we are again following this Markov assumption, right? So after applying the Markov assumption, we are just left out with the probabilities that are on just the earlier states, on just the previous states. So only the probabilities of the current state and its previous state, current state and its previous state will be required, right? So after applying the Markov assumption, we are left out with P of S. When we factorize this whole joint probability into factors, then that will be P of S. So in this initial S, we don't know the earlier state, so I am just writing P of S, or we may also write as P of S given nothing, right? Then P of, now we have written this one, P of this one, this S given the earlier S, given S, right? Then this one, for this one I am writing P of S given S. For this one I may write P of R given S. For this one I may write P of R given R, right? So this may continue with P of S given R dot P of R given S, right? So I may expand it in full form, so I may write it like P of S T. So instead of ST I may write it like S1, right? So S1 is equal to S. So don't confuse with this S1 and S. So S is sunny and S1 is a state. So Si is a state here, or St is state, and S is equal to sunny and R is equal to rainy, right? So S1 is equal to S, then probability of S2 is equal to S given S1 is equal to S, right? So this is corresponding to this term is corresponding to this, right? So I may write out for the next one P of S3 is equal to S given S2 is equal to S, right? So this is corresponding to this one, right? So I may write out for this one also, that is P of, so this is the last one, so this is S1, 1 2 3 4 5 6 7, so this is S7. P of S7 is equal to rainy given S6 is equal to sunny, right? So we can get these probability values from the table, right? So we are not conditioning these states on to much earlier states, like S3 is conditioned on S2 and S1, or S7 is conditioned on S6, S5, S4, S3, S2. So with the help of Markov property, we are just reducing the conditioning on only one state. So in that case, this probability table is sufficient, right? So we can finally get the value of P of S is actually a prior value or P of R. So P of S and P of R may also be given. P of S may be suppose 0 or 1 and P of R may be 0. So initially we are assuming that the day is always sunny. While starting we assume that the day is sunny and there is no rainy day. The probability of rainy day is 0. So P of S is 1. P of S is 1, right? So if some rainy day is starting, so the probability will be 0 because I am assuming that initially there could not be any rainy day, right? So if I start some sequence with rainy, so my assumption is that there cannot be any rainy day, so probability of any sequence starting with rainy will be 0. But if I take some small value, then starting with rainy will be, overall the probability will be small, right? So just for simplicity I am taking 0 and 1. So for the next value, P of S given S is 0.8, then again it is 0.8, then again it is R given S is 0.2, then R given R is 0.6, then S given R is 0.4, R given S is 0.2. So this is the total probability of this particular sequence, right? So this is how much? This can be this is very small probability, that is 0.0049152, right? So you must be wondering why we require to calculate this kind of sequence. So we must be rather interested in calculating the probability given a sequence. I would rather like to predict the probability of the next day, right? So given S S S R R S R, given this sequence, what is the probability of next state, right? So P of what is P of R, sorry, P of S8 is equal to R, and what is the probability of P of S8 is equal to S, right? So these two things are that will be required, right? So we know the conditional, right? But what will be the probability of any 8th day is absolutely rainy day or absolutely sunny day, right? So one could be this problem. So this problem is actually not an absolute one, but I may write it more clearly. So this is actually conditioned on the sequence, this S S S R R S R, this is S S S R R S R, right? So we are interested in these kind of probabilities, right? And then we can also calculate the absolute probability on given any third day, fourth day. What is the probability of S4 is equal to S, or S5 is equal to S, right? So we may also calculate, but we are more concerned with, given this sequence, what is the probability of this S or R, right? So this requires, again, in order to calculate this, we may know for this one up to this sequence what is the probability P of S given S S R R S R, right? For this we require P of S given S R R S R. For this we require P of S given R R S R, right? So for this we require P of R given R S R. For this we require P of R given S R, and we already know P of S given R, right? So we need to start from this initial and then calculate all these probabilities and reach up to this one. So now you must be wondering that we are applying, once we are applying a Markov assumption, and then we are again conditioning on chain. So we are applying Markov assumption for calculating these transition probabilities, right? So how do we calculate these transition probabilities? We must be given some kind of training data. This is some kind of parameters that are learned from a model, from a Markov model, right? So we may be given some kind of training data, a long sequences of 1,000 days or more than that. From those long sequences we may learn these probabilities, right? And we may arrive at a conclusion that these are the probabilities that are calculated from the training data, right? Now while prediction, we may be concerned in not applying the Markov property, that because we know what is the R given S or what is S given S, but we would like to know for some limited period, given that some limited period, what is the probability of next day, right? So given the probability of, say, suppose last 1 year, what is the probability of next month? Last 12 months, what is the probability of stock value for next 1 month, right? So we are not just concerned only just for the previous month, right? So because we would like to analyze the sequence, we would like to go into some variable time period, right? So that's why we require these kind of probabilities that are required while prediction. So this is a kind of inference or prediction, because we are predicting, we are given this only, this sequence of 7 states, we are predicting the 8th state, right? So these sequence are given as a test sequence. This probability table will be given as a training data, from the training data, and then you will be required to, so this is actually the Markov model, right? So we are not again yet reached up to the hidden Markov model. Let's see very quickly what is the hidden Markov model. So hidden Markov model actually produces some kind of observations, and the states remain hidden there. The states are hidden. So the observations are actually representing their states. The observations are representing their states. So whatever we are doing in these Markov models, we add some kind of observations to these states, and with the help of these observations we are able to identify the states. So in this example, whether it is a rainy or sunny, so there must be some observation which we will note down, and then we will come to know that this day is sunny. So like if temperature is very high, so there should be some kind of measurable, some kind of quantifiable property that would be treated as an observation, and that will be then in the back down task, it will be related with the state. So if I take the temperature, okay, so that temperature high or low may be related in some way, sunny, or similarly the measure of rainfall or measure of humidity. So I cannot measure the day is sunny. How would I measure? Right. So the sunny and rainy would be the hidden states. But I may measure the temperature, I may measure the humidity, I can measure it. But these are not the states, but these are the observations. Right? So I may take this sunny as a state, I may take rainy as a state, right? I may take the probabilities that are associated, the transition probabilities from sunny to rainy, from rainy to sunny, sunny to sunny, and rainy to rainy. Then there are some observations that are produced. So if I take the temperature, so I am taking the temperature again as an observation, right? So this temperature is an observation. So I am writing this T is actually a variable. If I don't write the variable, I write the value. So the value would be written like high or low. So high and low, right? So instead of writing, so this is sunny can exhibit, again it can exhibit two observations, whether the temperature is high or low, high or low. This is high and low. Similarly, rainy can also exhibit two observations, high, and obviously the probability from on a rainy day having high temperature may be low, may be zero, but we may take it into consideration, right? So now this is actually the hidden Markov model. This kind of modeling is the hidden Markov model, and if we draw its chain, so it would be a sunny day, okay, then a sunny day, then again a sunny day, again a sunny day. Let's take the previous example, sunny, 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 rainy, rainy, sunny, rainy. So this is rainy, rainy, sunny, rainy. So this is the Markov chain along with its observations. This is high, alright, the next day it is observed as high, again this next day it is observed as low, on next day it is observed as low, on next day it is observed as low, on this day it is observed as high, and on this day it is observed as high, right? So these are the observations. These are the observations. And these are the states. So this kind of modeling is the hidden Markov modeling. So we can now measure these temperature. We can also have humidity as another variable, right? So this can have more number of observations, humidity high or low, right? So that will make the system more complex. So for simplicity we are having only one variable in state and one variable in observation, right? So each of these states can have more number of values. This is a binary random variable, that is the same, sunny or rainy, high or low. We can have more number of values for a variable, right? So this is the hidden Markov model. So now in respect of hidden Markov model, We do have the one original probability table, that is transition probability table. Transition probability table. We have the priors, that is the initial values from which we are starting. We have to make some kind of assumption, right? And then we have from this hidden states or hidden observations, we have observation table. What is this observation table? It is the probability of, on a sunny day, what is the probability of high, on a sunny day what is the probability of low. So I may put on a sunny day the probability of high is very high, 0.9, this is 0.1, right? So on a rainy day the probability of high is 0.01 and the probability of low is 0.99, right? So I may convert this in the form of table. So on a sunny, so we are having only 4 values required to, so it can be written like this. So these are the states, these are states ST, states are sunny and rainy, and these are the observations are high and low. So on a sunny day it is 0.9, high is 0.9 and low is 0.1, and on a rainy day high is 0.01 and it is 0.99, right? So in this way we have, for a hidden Markov model can be represented by these 3 tables. If we are given these 3 tables, we can draw the sequence of these, and then we can that means from the training data we can take out these 3 things: transition probability table, observation table, okay, and then we may use these tables for prediction or inference. Again, now what could be the prediction here? So I may like to predict the next state again. So given this next observation, so because I can observe only, right? So I will measure the temperature here, whether it is high or low, right? Then what is the next state? This is required to predict. Now this kind of, again, will be having 2 things. It will be having conditioned on a set of states and condition of set of observations, right? So this will be P of S given S S R R S R H H L L L H H, right? So this is P of, I need to calculate P of sunny given S S S R R S R H H L L L H, right? So this is again day 1, day 2, day 3, day 4, day 5, day 6, day 7, day 1, day 2, day 3, day 4, day 5, day 6, H H L L L and H H, right? So this is 7. So now the things have become more complex. Alright. So this is the hidden Markov model, and we may now like to again predict some series of observations also, right? What is the next observation? Or we may like to calculate, given some current observation, what would have been the previous few sequences, right? Given the current observation, or the given current observation, suppose this is the given high. Okay, what is the, I have to predict a state. I would like to also predict what could have been the previous most likely sequence of states or most likely sequence of observations, right? I am only given with the current observation. So there could be different kinds of problems. We will discuss those in the next class, right? So one is like, what is the likelihood of these. We will take up those likelihood and decoding learning part in the later class. So this can be overall, this hidden Markov modeling can be divided into 3 problems. So we will take up that in the next class. 3 major category of problems. One is, for every problem we see how it is, how the model is learning, how the model is predicting, and how the model is something so here decoding is also required. So we have another problem, that is decoding. So we will take up these in the next class.